Today we'll be presenting Case 9-4, Broadcasting the Olympic Games. In this case, the WBC television network has won the rights to broadcast the next Summer Olympics. While this is a huge achievement, it comes with major challenges. WBC must manage an enormous volume of live broadcasts across multiple venues while ensuring smooth transmission back to its home studios. To handle this, WBC needs to upgrade its private network and efficiently route 35 gigabytes per second worth of data through multiple paths to prevent overload. Our analysis will explore the best strategies to optimize this process.
For case 9-4, letter A, by utilizing the entire computer network, what is the maximum bandwidth available in gigabytes for transmission from the general site of the Olympic Games, node A, to the home studios, node G? Set up and solve a linear programming spreadsheet model. So before we begin, we have to state the case facts, which is the problem is a maximizing flow problem. Like said, we need to find what is the maximum bandwidth available in gigabytes. Next is the source is node A, which is the general site of the Olympic Games, and the sink is the node G, which is WBC's home studios, where it is located. So at peak times, coverage of games will require 35 gigabytes flow from node A to node G. And last, total bandwidth required on each arc must not exceed the capacity. With this, we will use these case facts to formulate and solve a linear programming spreadsheet model.
Now, the problem for part A that we will be solving first is relatively simple. We simply have to find the maximum flow, maximum current bandwidth available for transmission from node A to G, of course, given our case facts and the requirements for this case. So for this problem, we will only have to find the current maximum bandwidth, provided our existing capacity. So we will not be needing any additional capacity or any additional costs for that in doing so, in order to meet the required 35 gigabytes flow from nodes A to G to cover the games during peak times. We simply have to find the current maximum bandwidth available given our existing capacity. So right here we have our from nodes to our two nodes. We have our A's to B, C, D, B's to D, E, F, C to D, D's to E and G, E to F, E to G2, and F to G. Our sync node is node G, where the home studios are located, and our source node is node A, where the games will be held. So given from the problem, we have our existing capacity right here, and we will have to find the flows for each of these arcs, which must be less than or equal to the existing capacity in finding the maximum available flow. Right here, we also have our given supply and demand, which are equal to 0. For this part, we don't have any required supply or demand or required flow for that matter. So we simply have to find the maximum flow. So these are equal to 0 for nodes B to F. Before we discuss our formulas and do our solver, right here are our range and our cells and our range names for these ranges and cells, which will help us easily distinguish the variables and the cells that are involved when we do our solver and our formula. For this part, we only have used one formula simply because our maximum flow is determined by the net flow for node A, which is also equal to the node net flow for node G. It is simply negative because our node G is the recipient of this flow. So right here, in order to determine our net flow, we had used the summing formula, summing the from the range from with the criteria of these nodes, so each of these nodes, and summing up their flow that we will be determining using solver minus the sum of our nodes this time. So that will be applied to all of these to cover the net flows of these. And so let us now delve into how we use solver to solve this problem. So right here we have our solver parameters. We have our maximum flow as the objective and set to maximum, since we have defined the maximum flow. And our changing variable cells would be our flow range, right here highlighted in yellow. Our constraints would have to be then the flow range, which must be less than or equal to our existing capacity, and our net flow, which must be equal to the supply and demand. So, which is why our nodes B to F have a zero net flow equal to those supply and demands. And simply we have our nodes A and nodes G providing our net flow for this problem. Hold on, let me just, there you go. So for our objective, as I've said, is the maximum flow. So once we solve that, this is now the solution that solver provides us, giving us a maximum flow of 27 gigabytes per second available for transmission from nodes A to G. This means Currently, with what we currently have in our existing capacity, this is the maximum that we can transmit from nodes or from our source node to our sink node. Now, in further of this problem, obviously we do not meet the requirement that is our 35 gigabytes in order to cover the games during peak times, which is why in the next problem we'll have to incorporate additional capacity and also the additional cost that will be incurred given that.
WBC needs to expand its network capacity to handle the peak requirements of 35 gigabytes per second from Node A to Node G. Currently, the network does not have sufficient bandwidth to support this requirement, so additional fiber optic cables must be installed to increase capacity. The expansion constraints include each network segment has a maximum additional capacity that can be installed. Each gigabyte per second of additional capacity has a cost in $1 million, which varies by segment, and the objective is to minimize the total cost while ensuring that at least 35 gigabytes per second of bandwidth is available from A to G. So the key considerations for this part is that WBC must decide which network segments to upgrade and by how much, and the solution must not exceed the maximum allowable additional capacity per link. And lastly, the cost should be minimized while ensuring the required total bandwidth is met.
For Part B, we are tasked to find the minimum cost of expanding the capacity of the network to handle the peak requirement of 35 gigabytes per second. Our spreadsheet model would be similar to Part A, but with different constraints and a different objective. So, to solve for the minimum cost, we are given additional data such as the maximum additional capacity per flow, the cost per additional capacity per flow, and the target flow of 35 gigabytes per second. So our objective in this problem is to find the total additional cost, which we get by summing the additional cost per flow. And to find the additional cost per flow, we multiply the increase in capacity and the cost per additional capacity. To find the increase in capacity, we subtract the existing flow, which we get from part A, to the optimal flow, which would be given by Excel solver. And for our solver, our objective cell is the total additional cost in K24. And then our goal is to minimize this value by changing the value of the flow represented in these yellow cells. And our constraints, we have three constraints, which are first, the increase in capacity must be less than or equal to the maximum additional capacity. And this increase in capacity must be greater than or equal to 0 because we are not permitted to decrease the capacity. We are only allowed to increase the capacity to handle the peak requirement of 35 gigabytes per second. And the third constraint is that these net flows must be equal to the supply and demand. And how do we get each of the net flow for each node? To get the net flow for each node, we have to subtract the inflow from the outflow. And to get the outflow, we take the flow which starts from that specific node and sum the corresponding flow values. And then for inflow, we take the flow which ends at that specific node and then take the sum of the corresponding values. So when we subtract the inflow from the outflow, we get the net flow. And for nodes B, C, D, and F, this must be 0 because 0 represents that the inflow is equal to the outflow. So their difference would be 0. And this means that nothing stays at that node. Everything flows from node A to node G, and that flow must be 35. And after running our solver with those constraints and objectives, we find the total additional cost and the minimum cost of expanding the capacity of the network to handle 35 gigabytes per second, which is 45.6.